Hi class, we're going to discuss the Born-Haber cycle. I strongly suggest you watch lecture 5 and 6. They both have to do with lattice energy and lattice structure before you watch this one. Okay, so it's a series of steps, chemical processes used to calculate the lattice energy of ionic solids, which is difficult to determine experimentally in a lab. So this is a special case if you look at it as Hess's law. Remember, Hess's law was from chapter 6. I'm sure all of you are scarred from chapter 6. And this involves manipulating equations for other reactions with known delta H values. So we change things around in order to get to the equation that we're interested in and the values that result from all of that. So I'm not going to spend too much time on lattice energy, but I am going to discuss it only on this slide. That's why I say for you to go into watching those lectures first. What is lattice energy? It's energy released, it's exothermic, and it's a large value. When a metal ion, so if we take a look down here, metal ion in its gaseous state combines with a non-metal anion in a gaseous state to form an ionic solid. The magnitude of the lattice energy relates to how stable the ionic solid is. A large value indicates a more stable compound. So these are very large values, and you can see that this one's way larger, so it's extremely stable. So this is what, for now, we're just going to call it Le. These are the lattice energies from ions in gaseous states that form solids. That's lattice energy. Again, can't be determined directly. So we take processes and we use them to determine what the lattice energy is. So we use ionization energy, electron affinity, bond energy, which hasn't really been too discussed, but it's energy required to break a bond. And enthalpy of sublimation is energy required to convert directly from the solid phase to a gas phase. We're skipping the liquid entirely. And then the reverse of the enthalpy of formation. So this here, oh, did I go too far? Oh, here it is on the next slide. This would be enthalpy of formation. We're going to use the reverse of that. And all of these together for the compounds we're interested in will give us the lattice energy. So we're going to take a look at this one first. It's already been solved. And it's easier if I show one first and then we work on one. That way you have a better understanding of what this is, and it makes your reading a lot easier. So the formation of solid potassium chloride from its elements is highly exothermic. So this is the enthalpy of formation. It gives off a very large number. And with it, we will have other numbers that will be given to us, or they'll be in a chart and you'll be able to pull them out. So here is the sum of the ionization energy, electron affinity, and then you can get the total of everything. Don't focus on this too much. The next slide I'll be able to describe things a little bit better. Ionization energy and electron affinity describe energy changes for particles in the gas phase. Everything is in gas phase. That's what some of the problems that we're going to get into, the Born-Haber, is changing everything to the gas phase. Why do we do it in the gas phase? Because when you do things in the solid, you're dealing with a structure that has a lot of attractions going on. And we would have to account for all of that. When it's in gas phase, gas particles don't interact with each other unless they have to, and then they rebound and they're on their way. So there's less interactions, which gives us a better better values than something that we would have to also take into account all those other interactions. Okay, so all of this, by the way, I got all these, if I didn't mention it before, I've recorded this several times and had to delete it. These are all PowerPoints that are listed. This is all from chapter 9. I don't normally use the PowerPoints, I use my own, but these had the best examples. So these are all in your slides. All right, so step 1, the reverse of enthalpy. There are 5 steps. They may seem very complicated. There actually are not. Once you understand the 5 steps, then you'll understand what you need to look for. And all it is getting the values and then adding them all together. That's it. Nothing difficult. You've done far more than this up to this point. So we're going to take the reverse. The key thing is the reverse of enthalpy of formation. So it's going to be the opposite sign. So we flip the reaction, because what we're going to do is we need to get everything in gas state. So we need to get this out of solid, and then we're going to separate these and get them in different steps to gas state. So if we look at the first one, the enthalpy of formation was negative 437. We're taking the reverse of that. So you can either list this as delta H1 or actually keep it as delta H with the F, standard F. Standard enthalpy of formation, sorry. Now we have this separated into potassium and chlorine or chloride. The second step is the conversion of getting potassium to a gas from a solid. The best way that I can tell you how to do these steps is focus on one atom first and then tackle the other. So usually, and how it is listed in here, is they tackle the metal cation, they get it to the metal cation, and then they tackle the anion. So that's how I'm going to show you. So we focus now is on the potassium. So next thing is a conversion of potassium solid to potassium gas. That's sublimation. We are totally skipping the liquid. And there will be a chart or something given to you so you can determine what this is. Now you can either leave it as delta H2 or the enthalpy of sublimation. Step 3, we're still working on potassium, is now it's in gas, but we need it in as an ion, because when we're looking at the lattice energy, this is really the lattice energy of an ionic compound. So we need to get this into ionic form. So we're going to go from keeping it in gas to a neutral to a cation. That's the ionization energy, pulling that electron away. So here is the value for that. Step 4, the formation of chloride gas to, the formation of single chloride gas from a diatomic molecule. So now that we've gotten potassium exactly in the ionic form we need, now we take care of chloride, which is only technically, it's got 2 steps, where this one has 2 here, this has 2, and the first one is just separating them out of an ionic compound, breaking that bond in a sense. So here they have the half. Why do they have a half? Because we only want one of these. This will divide this and cancel out and only give us 1. So this is the bond energy. We are breaking the bond between Cl and Cl. And you get all these values will be given a chart or something. You'll just have to determine what you need to do. Do these steps have to be in this order? No, they do not. But it's best if you learn it in one way and you keep it that way, because then you do not make mistakes. You tend to lessen that if you keep it as a routine. So here is our bond energy, and we have a value. These, and if you notice, I'll look at that at the end. Now we have it as a gas, but we need it as an anion. So the addition of an electron, the electron affinity of chloride, and that is the electron that was removed from potassium is going to the chloride ion, and that is given here. So let's take a look at this. We have the reverse enthalpy of formation. It is endothermic. We have a conversion of enthalpy of sublimation. It is endothermic. So all of these need energy to do these changes. Ionization energy is endothermic, and then bond energy needs energy in order to break bonds. That's also endothermic. But the addition of an electron is exothermic. So one of these is going to be exothermic, but that's okay. You're still going to add them all together. Now, if we look here, your book has this, this formula. It's in your book, and it's also in your book as this way. So it depends on how you list it. You can use this, or you can use this. I use this because it allows me to know that I've taken care of each one of these, and I can confirm by just looking at them what it is I need to do. Now plug everything in to that formula, and the lattice energy of potassium chloride is negative 717 kilojoules per mole. This works for a +1 metal cation and a halogen. So that's what you're always going to be dealing with on these if it's given to you. So let's now, I have a couple problems here. Write the chemical equation that corresponds to the lattice energy. What is the lattice energy of calcium chloride? Well, the calcium lattice energy is the energy released when gas phase ions are converted into a solid ionic compound. So it is, think of it as a dissociation, make them ions, put them as a gas, and then the product is solid. So this is very easy if you think about it not as lattice energy, but more as disassociating it, but then showing the reaction of it coming together. Just got to remember you're dealing with ions, and they have to be in gas state. Okay, so we're going to do this problem. Use the values listed here to determine the lattice energy of Mx and identify the compound. This sounds like it's very, very difficult to do, but the values have already been given to you. Everything's been given to you here, so it is not as difficult as it may seem to be. The hardest part is if you're working on paper is you got to make sure you don't make a mistake, and you got to look at a chart if the values are not given to you, that you have to look at all the charts to make sure you're picking the right value under the right whatever it is, ionization, electron affinity, and so forth. So let's get through this. So they've given all the values, but these are not in order. If you notice here, they're not in order of the way that I would have them. This is the Born-Haber cycle, and this is what's, they would talk about if you would probably have to draw this out. I'm not going to expect that. But these are the steps, and you see the energy goes in, some energy comes out, and then that difference is the lattice energy. So that's what this is. It starts here, goes through to the gas state, and it should be this is a gas, not an ion yet, but this one is. Then we get the electron affinity, gets it to both ionic states, and then the difference is the lattice energy. So I numbered these. I kept them exactly how they were presented here. I just numbered them so you can see exactly what the states look like. And you should become very familiar because there's homework that's going to match this. And the more that you understand this, the homework is not going to be difficult at all. It's not really, the steps don't really change. So the wording may be difficult, but if you know the steps, you can pull stuff out. Chemistry is nothing but making things just more difficult, it seems like. And I didn't do that. That's the book and stuff. I'm trying to break it down to hopefully help make more sense out of it. Okay, so you were given all the values here on this previous one. So it actually doesn't even matter how you add them together, but I keep everything in a form that I can remember exactly where it goes, because this would help me if I had to look it up. So if I know this equation, which by the way isn't going to be given to you, so you should make sure that you have it. But then if you know that this one has to be here, this has to be here, then you've taken care of every single one of these processes that needs to be involved in this. So you plug them all in, and then for this, the lattice energy of an ionic compound is negative 788 kilojoules per mole. So all we need to do is look at a chart and see which value that has. So this is in your book. This is table 9. It says it here. And this is negative 788, which is right here. So MX is sodium chloride. And that's it. Thank you.